Hi, I'm Ben-Yaakov. This presentation is entitled A Thermal Model of Film Capacitors. This video was created in collaboration with Evgeny Smidotsky and Oded Arlevsky from IRP Systems Israel. The problem that we are addressing in this presentation is to develop a model for the thermal behavior of a film capacitor, and in particular MKP, polypropylene capacitor, for any ripple current profile. That is not just for a continuous current ripple or continuous pulses, but like current going up and down in a certain profile. This information of the behavior of the capacitor under these conditions cannot be obtained today from the datasheet. We are assuming here that we have sort of a switcher, a converter, inverter, which is injecting into this bus capacitor. This is like a representation. Into this bus capacitor, a ripple current, a high current, and we are asking what will be the temperature, and of course what is of interest is the lifetime of the capacitor under the particular operating condition. So what we have here is a body. Here there's a capacitor in which power is dissipated, so heat is building up and temperature is building up, and therefore there is a sort of a imaginary hotspot which we are referring to, which is the hottest point, and it has a very important effect on the lifetime. And here we see, actually this is from the datasheet, and these are the hotspot temperature. This is the voltage of the capacitor, the working voltage normalized to the rated. That is, if you have a capacitor of say 1100 volt, then if you work at 1100 volt, this would be 1. But if you work at a lower voltage, that would be like a fraction of this 1. And here is we have the lifetime. So for example, if we have a capacitor in which the hotspot is 105 degrees centigrade, you see that if you work at a 0.8 of the rated voltage, you can expect a lifetime of 10,000 hours. But as you can see that you cannot work beyond 0.9 because of breakdown, as a matter of fact. So this information is extremely important for safe operating condition as well as the lifetime. Now the simplest model, thermal model of such a case will be a current source which represents the power dissipated within the device, a thermal resistance to the ambient, and here the thermal resistance which is emulated by a electrical resistor in this equivalent circuit, and the temperature is emulated by a voltage. We also have here a capacitance which represents the thermal capacitance of the body, because in steady state you just have to worry about this resistance, thermal resistance. You have a power coming in like a current flowing here. So if you know the temperature here, you can find the temperature here by multiplying the current times this thermal resistance or resistance, adding it to the ambient, and you get the hotspot temperature. But if you have transient, then you have to take into account that some of the energy is absorbed within the body as a heat, so this will affect the buildup of the hotspot. So the parameters we are concerned here is the thermal resistance, which is emulated by a resistor, the power by a current source, the thermal capacitance by a capacitor, and the units here are joule per degree centigrade. And for getting this information, you need to know the material, the weight, and the specific heat capacity so that you can find out what is the thermal capacity. Let's have a look now how a typical film capacitor is built. Basically, we do have strips of the film material, polypropylene in this case, which is metallized. There is a layer of metal on it. You see that the metal is exposed here at the end and also here. It sort of comes out a little bit and comes out a little bit. We can see it here. And then we have this sort of a sponge type, it's called scoopage, like a gooey material here, which is added here at the end and this is a conducting material, so it makes a contact with these ends, and in fact the input is coming from here, the current is coming from here into all the layers here of this capacitor. So we can see it here a little bit better. We see the layers here, and here we see the end. This is this to which we are actually attaching the leads for the contact. Now this is not round, it's been flattened, so it will go into a case. And in this case, of course, the heat is now generated throughout this volume because of the losses of the dielectric material, that is the polypropylene. And then this heat is transferred to the outside through here, like this way. And also, of course, this way, actually this way. This is half of, actually it's a quarter of the volume here. It goes this way, or you might say this way. Now, in a body like that, you probably would like to have a more sophisticated model, which would be like a leather, like cover type leather, in which you actually take into account that there are sort of compartments here. It's not just one volume, but you have layers and layers. Obviously you can make too many of these, so you can break it down into some units. Each one will have its source for the power, the capacitance, heat capacitance, thermal resistance, and then we have the thermal resistance going all the way, as I have said, this way, okay, this is this way, and then also to the side, which is going this way. Now we have arbitrarily assumed that for a body like this, the ratio between this one and this one is like 0.2. Obviously, this is just a approximation. As you'll see, it's really not needed, but I'm starting with this more elaborated model. So we have these layers here, we have these compartments. Each one is represented by this basic thermal unit. So to develop the model, we need the capacitor type, the weight, thermal capacitance, the hotspot to ambient thermal resistance. Usually for these capacitors, this is given between hotspot and ambient. And then the frequency, ESR, ambient temperature, and then of course if we are concerned with specific application, we like to know what is the lifetime that is required from this capacitor, what is the bus voltage, and the profile of the current, that is, how is the current going up and down as a function of time. So to build up the model, we consider this volume here, which has a certain mass to it. Power is coming in due to this current, and the power is I square ESR. Volume is just a product of these dimensions. The mass is the volume times the specific gravity, and then we assume some filling factor, that it is all the volume here is not filled with polypropylene. There's some void, so we sort of assume a filling factor. So the heat capacitance is the specific heat capacitance times the mass times this filling factor. And then, of course, we need to know what is the material, and assuming a specific heat capacitance. So in order to develop the model, rather than handling the whole unit, we sort of break it down into half. So we look at half of it has half the thermal capacitance, half the power, and double the thermal resistance, because the total thermal resistance is of both sides, and we are now considering only half of this unit. Here it is, this is half of the unit. So we're assuming that we have this leather, and that the total thermal resistance from here to here is the one specified in the datasheet. So this will be this elaborated model, and this will be the very simple poor boy model with just one thermal resistance and one capacitance. And what we are going to do, we are going to compare these two and to see how important is it to break down, in this particular case of this film capacitor, how important is it to break down the thermal model into these units. So just arbitrarily we have chosen to break it down into a binary fractions, and the reason is that we have volumes of different sizes. Here the volume is smaller, and then we have a larger, and then a larger. So here we have a larger thermal resistance and a smaller capacitance, and then we have a certain power source, and then as we go here, the power source is increasing, capacitance is increasing, and the thermal resistance is reducing. And we assumed here a sort of a binary law. So we have it here, you see that here the thermal resistance, then it's sort of going down, capacitance is going up, and the sources are also going up. So this is just, again, arbitrarily dividing it into these 4 sections, and then eventually we're going to compare it to the single unit. Now the information that you need, of course, this is the type of capacitor we are working with, 60 microfarad, 1100 volt, switching frequency, the ripple current. Now we have a profile in which we have continuous current, then we have a maximum ripple current of 37 amp for 60 seconds, and then it sort of repeats itself every 180 seconds. So it's kind of a representing sort of a operation of, say, a inverter for a vehicle or something like that, that you have an average current, then you have from time to time higher current. The ambient temperature is soon to be 65, voltage 850, and we would like to have a 40 kilo-hour lifetime, and the 850 volt is 0.77 of this capacitor, which is 1100 volt. Now the thermal information, or thermal related information, is the ESR, which is given. The total thermal resistance from hotspot to ambient is also given. Of course, the volume. We assume that most of the volume is occupied by the polypropylene, which has this specific weight. This is the mass. This is the specific heat capacitance of the polypropylene, and this will be the heat capacitance of the body itself. So now we can run a simulation, putting all these numbers inside, and we can run it for a particular case that we have said at 20 amp, continuous 37 amp, and this is already the power. This is I squared times R, and you see that the power is starting from, there's a base of 0.9 amp. It's not amp, it represents the watts, the power. It is just a question of the behavioral model that we are using. So the power is emulated by actually current. And then we have peaks, and they're sort of repeating themselves. And here it is. So what we see here is the hotspot temperature. So here is the hotspot temperature, the highest temperature in this array. So we see that the average is about 107, and we go to a peaks of 108. This is due to the pulsating, and this is due to the average power. Okay, this is the volt represent here degrees centigrade. So now we got the number, and this is 107 degrees. So we are just a little bit above 105. If it would have been 105 and we are working at 0.77, it would have been this number, but we are not 105, we are 107, so we have sort of extrapolated here, and we got 8,000 hours. So for this particular case, the model prediction is 8,000 hours based on this model. Now the question is, do we need this many sections, or is it enough to have one section? So now we run here from the beginning, from time 0 the buildup of the temperature, of the hotspot temperature. And this is superimposed. You have 4 units, a ladder, 2 units, and 1 unit. And what we can see is the differences are really small, especially for this when it stabilizes. So our conclusion is that for this particular case, a very simple model of just one section here, one capacitance, and one resistance is good enough. Okay? So it really simplifies the matter very much. This is a number that we got from the data sheet, the thermal resistance. This we can estimate from the volume and weight and the specific heat capacitance of the polypropylene with assuming some filling factor. So everything is okay. So things are really very simple, and we see that we get pretty good results as compared to this more complicated model. Now, in fact, after developing the model, we found that there is a paper which also developed a model which is on the surface looks very similar. I will not go into it, very similar. But development of the parameters here is rather elaborate, and again, I'm not going to cover it. Whoever is interested, this is the paper. And they had done it on this type of capacitor. This is not a specific capacitor, but this is this type. It's a cylindrical capacitor. It's also a film capacitor, okay? And here, what they did, they somehow managed to measure the hotspot temperature, and this is the broken line, and this is the model prediction, okay? The continuous line is prediction, and this is measurement. Now this particular unit, this is by the way the capacitor, it weighs 1.1 kilowatts, a big capacitor, and here is the thermal resistance between the hotspot and ambient, okay, it's given here. And from the volume, we can find out that the heat capacitance is 2068 joule per degree centigrade for this particular one. Knowing that the single stage is good enough, we now compare the result from this paper, which is independent, completely independent. It's another model with our model, or I think it's a simple model. With these numbers, okay, we have just 2 numbers here, and the source is of course the power dissipated, and this depending on the profile. And here what they are showing is a startup, just a startup, that is, you start feeding the current, and here are the results of our model for different currents, okay? So this will be the time, and this will be again temperature rise. Okay, it's starting from the ambient of 25 and goes to up to 50 something for 70 amp. Okay, this is steady state, and this is the turn on transient. And looking more closely at the very beginning. Now we compare the result from the paper, the model developed in the paper, or shown in the paper, I should say, to our result. Again, this is the model that they had. This is the measured, and the dots are our result from our model. And as you can see, in fact, we are even better than the model that they have developed. With the very simple model that we have, we are very, very close to the measurement. Looking up, zooming into the beginning, I mean, it's here. They also got this information here for the very beginning. You see that again that our results are pretty close to the measurement. Here it is, and here it is. The broken is the measurement, while the model in the paper is a little bit far away. So we can see that the model now verified independently by another study, completely different model, but there are some lab measurements, which is very, very important, of course. So it would appear that the model is performing very well. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.